Hello, and welcome to the fifth and final video about what derivatives tell us, where we talk about how to use the first derivative to tell if a function is increasing or decreasing, and how to use the second derivative to tell if a function is concave up and concave down. And we can also use the first derivative test to tell whether a critical value is a local minimum or a local maximum, or neither. And now we're going to look at using the second derivative test to tell you if a critical value of the first derivative represents a relative or local maximum or minimum. So the second derivative test says if your second derivative is continuous on the interval you're working with that contains some value of x, let's call it c, and c is a critical value, a zero of the first derivative, then what we know is if the second derivative at that critical value is positive, then we know your function is concave up. So you have a minimum at c. Now that might not make much sense for the moment because you think up doesn't usually mean minimum, but let's look at what we mean when we say concave up. Concave up means the curve is shaped in general like that. So you have either a top or a bottom if you have this case. And as long as this, and if you have this case where you are at a point where the first derivative is zero, so your tangent line is horizontal, and the second derivative is positive, it means the shape of the curve is like this, you must be at a bottom. So that's why a positive second derivative, meaning your function is concave up, shows you are at a minimum. I even sketch that when I do the second derivative test just to keep that in my mind. If the second derivative is negative, the function, I'm drawing the functions here, this is f of x. The function is concave down if the second derivative is negative, which means it's kind of like a tipped upside down bowl, which means if this is what f of x looks like and you're at this point here where the tangent is horizontal, you must be at a maximum, a relative or local maximum. Now, if you have a first derivative equals 0 and at that same point second derivative equals 0, you have no conclusion. So if the second derivative is 0, you can't use the second derivative test. Now, in example 7, in your guided notes, we're supposed to use the second derivative test to find the value of x. We don't need the y coordinate when we're done, where local extrema meaning minimum or a maximum of the function exist. You don't have to find the actual maximum, and that would be the y coordinate, the actual maximum, and you find that by going back into the original function. Because remember, we're using these tests to tell us things about the function. I think it's easy to get confused because you have a function that looks like an equation, a first derivative that looks like an equation, a second derivative that looks like an equation, and we analyze the first derivative and the second derivative, but the reason we analyze them is to tell us about the function. So, our function is x cubed minus 12x minus 5. I've already typed out the first derivative here. This is pretty simple polynomial. And then when you get 3x squared minus 12, that factors to 3 times x squared minus 4. That factors into the sum and difference of squares. So either 3 is 0, but that's never true, so that doesn't give us any potential zeros of the first derivative. Or x plus 2 is 0, or x minus 2 is 0, so we get at x equals negative 2, this would be 0. At x equals positive 2, x minus 2 is 0. So these are our critical values that we need to check. So now I want to know whether these are a maximum or a minimum. So I will use the second derivative test. I could make a sign chart and put negative 2 and 2 on a number line. But what I'm going to do is I'm going to perform the second derivative test. So the second derivative of 3x squared minus 12 is 6x. So I take each critical value. I have negative 2, so I find f of negative 2, and I find that this is negative. The second derivative is negative. So my function must be concave down. Concave down looks like that. So if this is x equals negative 2, that must be a local maximum. Then I put in the other critical value and find the second derivative at x equals 2, and I find it is positive. Positive second derivative means the function is concave up, so if I had a horizontal tangent line, I must be at a bottom, which we call a min. It's a local min. So that's using the second derivative test. If the second derivative is easily found and is defined and not equal to 0 at your critical values, I actually find this easier than a sign chart. Now, if you are also being asked where is the function increasing or decreasing, the first derivative sign chart is helpful for that anyway, and I would just use the first derivative test if I had a choice. I do not believe that I force you into either one, but you must justify your work using either the first derivative test or the second derivative test when you are asked to find local extremes of a function. You can't just graph it and say, I used my calculator. You have to use one of these two tests. Okay, let's move on. We believe we have another example here. Yes, we do. Okay, this one is student practice. You should try this one. Take the first derivative. It's a little trickier because it's a product and it involves e to the x. And then follow the process I did above. And when you're done, open this video, stop the video, do the work, and open the video and come back. All right, I'm trusting you that you just came back. Here's our function, and the derivative I took using the product rule. The first function is e to the x. The derivative of x minus 4 is 1, so I get e to the x times 1. E to the x is its own derivative. The multiplier in front of the x is a 1, so I just don't need to multiply it by the 1. So I have the derivative of e to the x times the second function x minus 4, and then when I multiply this out, I'd see I have 1 e to the x here, I'd have negative 4 there. This comes out to e to the x times x minus 3. Now, e to the x times x minus 3, you would solve by writing both factors equal to 0. But this is never true, because a positive number raised to an exponent is never 0 or negative. It's always positive. It's non-zero. Okay, so that's why we end up ignoring. It feels like we ignore it sometimes, but since it can't be equal to 0, we don't need to consider that factor. So I just get this factor, gives me x is 3. So now I take the second derivative. I'm taking the derivative of this. It is also a product. The first function is e to the x. The second function is x minus 3. And again, the derivative of e to the x is just e to the x. The derivative of x minus 3 is a 1. So it falls out very similarly. And I get e to the x times x minus 2. So I don't need to find the zeros of this. I would need to do that if I was looking for the inflection point. But I've been asked just to use the second derivative test to find relative or local, depending on which text you're using, maximum or minimum. So I need to go to the critical values and put that into the second derivative and find the sign. So the sign is positive. That means the f of x is concave up. So f of x has a shape generally like that. It doesn't need to be this whole thing. It could just be some little piece of that, I suppose. But the shape is like that for concave up. And I already know, because I'm at a critical value, that I am at a place where the tangent line is horizontal. So I see that as a minimum. That is a local minimum. So that's what this statement says, and that's how you would do that problem. So that's the second derivative test for local extremes. That is very helpful if the second derivative is easy to find. It's not very helpful if it isn't, or if you've already had to make the sign chart. Okay, thank you for joining me for this fifth and final video of this section. Email me your questions.